You're standing outside on a clear night. You look up. Somewhere up there, past the smear of the Milky Way, past the planets you can't see with your naked eye, there's a star so big that if you put it where our sun sits right now, it would swallow Mercury. Then Venus. Then Earth. Then Mars. Then Jupiter. Still expanding. Still growing. It would keep going past Saturn, past Uranus, past Neptune. And when it finally stopped, the outer edge of this star would be sitting somewhere beyond the orbit of Pluto. Our entire solar system. Gone. Swallowed whole by one single object. And it's real. It exists. It's sitting in our galaxy right now, burning with the energy of 10 billion suns. So what is it? And why have most people never heard of it? That's what I want to show you. Here's the thing about our sun. We talk about it like it's something enormous. And by human standards, it is. You could fit 1 million Earths inside the sun. 1 million. If you drove a car at highway speed from one side to the other, it would take 176 years. But here's what most people don't realize. Our sun is a runt. Among the hundreds of billions of stars in the Milky Way, our sun ranks in roughly the top 10% by mass, which sounds impressive until you understand what the other 10% looks like. Because at the very top of that scale, there are objects so extreme that astronomers genuinely struggled to believe they were real when we first found them. Stars so massive that our current understanding of physics cannot fully explain why they haven't torn themselves apart. We call them hypergents, and they are nothing like anything you have ever imagined when you thought of a star. Let's start with a star you may have heard of, Betelgeuse. It's the red-orange dot at the shoulder of the Orion constellation. If Betelgeuse replaced our sun, it would engulf every planet out to Jupiter. For most of human history, that sounded like the ceiling, the absolute upper limit of what a star could be. But here's the key. Betelgeuse isn't even close to the largest stars we've found. In 1997, a team of astronomers studying a star-forming region called the Carina Nebula, a violent, churning cloud of gas and dust about 7,500 light-years from Earth, cataloged a star designated Eta Carinae. What they found stopped them cold. This wasn't just a large star. This was a star between 100 and 150 times the mass of our sun, shining with 5 million times its luminosity. 5 million times. The math barely fits inside the human brain. But Eta Carinae is still not the record holder. That title currently belongs to a star called UY Scuti, located roughly 9,500 light-years away in the constellation Scutum. In 2012, a research team at the University of Bonn measured its radius at approximately 1,700 times the radius of the Sun, 1,700. If you placed UY Scuti at the center of our solar system, its surface would extend to a point just beyond the orbit of Saturn, about 1.3 billion kilometers from the Sun. Now, some of you are thinking, bigger doesn't mean more powerful. Fair point. Size and luminosity are different things. You're right. But here's where it gets interesting. Because the star that wins on sheer energy output is even more disturbing than the star that wins on size. It's called R136A1. It sits inside the Tarantula Nebula in the Large Magellanic Cloud, a small satellite galaxy orbiting our own. In 2010, a team led by astrophysicist Paul Crowther at the University of Sheffield analyzed R136A1 and arrived at a number that broke all existing models. This single star burns at roughly 8 to 10 million times the luminosity of our sun. Not 5x, not 100x, 10 million times. It is, by every measurement we have, the most luminous and most massive star ever confirmed. We know this because astronomers used the Hubble Space Telescope to dissect its light, a process called spectroscopy. And what they found in that light told them the temperature at the surface was around 40,000 Kelvin. The surface of our sun is about 5,778 Kelvin. R136A1 is running 7 times hotter and releasing energy on a scale that makes human comprehension physically uncomfortable. Here's what modern people find hardest to understand about hypergent stars. They don't behave like stars are supposed to behave. Our sun is stable. It has been burning, slowly and steadily, for about 4.6 billion years. It will keep burning for another 5 billion. It is, in cosmic terms, reliable. Boring, even. You could set your watch by it for the next few billion years and never be surprised. Hypergents are not boring. A star like R136A1 is burning itself alive. The radiation pressure from its own energy output is so intense that it constantly blows material off its surface, not as a gentle solar wind the way our sun does, but as a roaring, continuous eruption. In one single year, R136, a 1 loses an amount of mass equivalent to several times the Earth. Not in a flare, not in an event. Just as a baseline, just Tuesday. Eta Carinae is even more dramatic. In 1843, human astronomers watched it erupt in what's called a Great Eruption, a violent outburst that briefly made it the second brightest star in the sky from Earth, visible in broad daylight, and ejected a mass of material now estimated at between 10 and 40 times the mass of our sun into space. We can still see that ejected shell today. Astronomers call it the Homunculus Nebula, a glowing, peanut-shaped cloud of gas and dust moving outward at 650 kilometers per second. Here's the part that gets me. We still don't fully know why that eruption happened. We have theories. We have models. But the actual mechanism that made Eta Carinae do what it did in 1843 remains, as of right now, an open question in astrophysics. These stars exist in a zone where our equations start to strain. They are so massive that gravity is in constant war with radiation. Most of the time, this war ends when the star simply destroys itself. Then, after just a few million years, something changes. Our sun will live for roughly 10 billion years. A hypergent star lives for approximately 1 to 3 million. That sounds long until you compare it. Our sun is 10,000 times older. A hypergent burns so bright, so fast, so extravagantly that it exhausts its fuel in what is, on cosmic timescales, an eye blink. And when a hypergent runs out of fuel, it does not gently expand into a red giant the way our sun will. It does not quietly collapse into a white dwarf. It explodes. Completely. Violently. In an event called a core collapse supernova, the star's iron core collapses in less than a second. Less than 1 second for an object containing more mass than our sun, triggering a shockwave that tears the entire star apart. The explosion releases more energy in those first few seconds than our sun will produce in its entire 10 billion year lifetime. The most massive ones may not even stop there. They collapse so completely that they become something even stranger, a black hole, a point of infinite density, a place where our equations don't just strain, they break entirely. Here's what that explosion leaves behind. When a hypergent goes supernova, it seeds the surrounding space with heavy elements: oxygen, carbon, silicon, iron, gold, uranium. Elements that cannot be forged any other way. Only inside a star, massive enough to fuse atoms beyond iron, and only released when that star violently dies. The calcium in your bones was forged in a dying star. The iron in your blood was born in a stellar explosion. The gold in any ring you've ever worn was created when 2 collapsed stellar remnants spiraled into each other billions of years ago. These elements drift through space for millions of years, cooling and condensing until gravity pulls them together into new clouds of gas and dust. Clouds that collapse into new stars, new planets, new solar systems, possibly new life. Hypergent stars don't just exist. They die, and their deaths build the raw materials for everything that comes next. They are the universe's most violent factories. Tonight, you'll go outside and look at a sky full of dots. Most of them will seem identical, static, permanent, eternal. But somewhere up there, right now, a hypergent star is burning 10 million times brighter than our sun, steadily destroying itself, running out of time at a pace we can barely calculate. It has maybe a few 100,000 years left. Maybe less. In cosmic terms, it's already basically over. And when it goes, the shockwave will tear through neighboring gas clouds and compress them, triggering the birth of new stars, new planets, new systems, possibly new observers who will one day look up and wonder where they came from. Most people assume stars are permanent. They're not. They're the universe's most efficient machines for turning hydrogen into everything else. And the bigger they burn, the faster they spend themselves, and the more spectacularly they give everything back. The largest stars don't last the longest. They live the brightest, die the fastest, and leave the most behind. You're made of what they left.